Hey there, chemistry students. This is Ms. Ruark. We're starting quantum theory, so we're going to start looking a little bit more in depth into the atom. All right, so locating electrons. It is known that, excuse me, electrons form what we call a cloud around the nucleus. Okay, they are all around outside the nucleus. They are not inside the nucleus. They are outside the nucleus. And what is a cloud mostly made of? Air, right? Yes, empty space. All right, so the most stable configuration for any atom is going to be a full valence shell. Valence means the outermost energy level. Okay, so all of these electrons want a full outer valence shell. They want to hold the most electrons they possibly can in their outside electron or in their outside energy level because it makes them stable. They're not going all crazy trying to steal everybody's electrons if they have a full electron shell. Right? And so how do we do these? Well, we can use the periodic table and we can describe the location of electrons, which allows us to predict how an element will behave with others. Okay, just like we try to predict how you all behave with others. Well, we can do that with electrons as well by locating their electrons. All right, the Bohr model was the first model that came up of a, well, it wasn't the very first one. First there was the billiard ball model, which said that it was just an atom. It was completely, you couldn't break it down. And then after that model came the plum pudding model, which was J.J. Thomson, and he said that there was a bunch of negatives thrown into a positive mess. So like if you would think of pudding would be the positive mess or the positive matter, and then if you took raisins and threw it into there, there would be your negative electrons just kind of randomly thrown in there. Well, then after that, they figured out, hey, there is this thing called a nucleus, thanks to Rutherford, and it has a positive charge. And so the plum pudding model was discredited. But then this guy, Niels Bohr, came along and said, hey, protons are in the inside with the neutrons, and the electrons go around the outside, and they go around in these nice, pretty little energy levels. So they actually orbit the nucleus, kind of like the planets orbit the sun. Right? And it says in his model, he says that each ring is described by a specific amount of energy. And he also said that these energy levels are distinct and separate. He said that the electrons stay in these nice, pretty little energy levels, and they don't really go anywhere. They just go around and around and around and around. Right? Well, if we know, according to Bohr's model, if we know the periodic table and we know, the energy levels and the rows and the columns, then we can use that to sketch a nice, pretty little model of the atom and all the electrons that are in each energy level. And that was great and all, but guess what? With every model comes limitations. And we said, it's not completely correct, because electrons don't move in concentric circles. They move around in what we call orbitals. Okay? Orbitals are three-dimensional regions of space. So 3D regions of space. Oops, three-dimensional regions of space. So now we think of it as a cloud. Okay, and there's a guy named Schrodinger. Some of you might have heard of Schrodinger's cat, where he did some work with a cat, and yeah, you can look that up. Okay, but Schrodinger did some work with this, and he came up with an equation. I went too far. He came up with equations that describe the probability of finding an electron in any given location. Well, there's another guy named Heisenberg who said, hey, guess what? You can find the electron, but you can't determine its velocity. Or if you figure out its velocity, you can't figure out where it's located at because it's already gone. Okay, we're kind of delving a little deeper than we need to. So all we need to know is that we can use the periodic table to determine the electron location. So the electrons are mapped out on the periodic table. And each section of the periodic table represents a different orbital shape. You can have the S's, the P's, the D's, and the F's. Okay, so we have S orbitals, P orbitals, D orbitals, and F orbitals. All right, and over here is just a more modern view of what the atom looks like now, whereas here is your electron cloud, is what we call them now, and those would be represented by your orbitals. All right, so here's your periodic table. Go ahead and pause it. Get out your periodic table if you don't have it yet because you need to draw on it. Pause it. Okay, go. All right, so our S, our P, and our D, and our F orbitals. If you take your periodic table, these first two columns here are going to be your S orbitals. And S stands for sphere, so it's a sphere. Okay, it's a sphere. It's like a big ball. All right, these here are going to be your P orbitals. Okay, your P orbitals. So S would be your sphere, looks like a ball, and then P would be your. It actually stands for parabola, so it looks like an infinity sign. Okay. Notice how I did not include helium in the P orbitals. Helium should be, according to this, right here, so it fills up the S orbital. Okay. Then you have your swimming pool area, and this right here is your D orbitals. And then you have your lanthanide and your actinide series, and these are going to be your F orbitals. Okay, so make sure you have those drawn on your periodic table. Moving on. Okay, quantum theory. So Schrodinger and some other people came up with this thing called quantum theory, and it's based on quantum physics. And we're not going to get into that, but if you want to, you come by and see me. We can talk about it all day long. Okay, so quantum theory suggests that the electrons are in orbitals, these 3D regions of space, and we can use 4 numbers to tell the probable, keyword there, probable location of an electron. So you have your first quantum number, which is the principal quantum number, and it's designated by an N, and it just tells us the energy level of that particular electron. That's all it does. Okay. Then you have your angular momentum quantum number, which is designated by a cursive L, and it tells us the orbital shape, or the shape of the orbital. So here's your S, your P's, your D's, and your F's. Okay. And let's come back up. Principal quantum number, energy level, excuse me, and you can tell that from the row or the period of the element. All right, your M sub L is your magnetic quantum number, and it tells us the orbital orientation around the X, the Y, and the Z axis. Now, of course, there's going to be more to it than just this, but I'm giving you the bare bones of this, okay? And then your M sub S is going to be your spin quantum number, and it tells us the clockwise or counterclockwise spin of the electron. All right, so we need to know that because each orbital can hold 2 electrons and no more than that. No more. It can hold less, but it can't hold more. So don't try to put more than 2 electrons in each orbital. It doesn't work. Right? And when you put those 2 electrons in there, they must have opposite spins. Must have opposite spins. You can't have 2 of them going in the same direction, and then the orbital spins out of control, right? No, I'm just joking. Okay. All right, so let's break these down a little bit more. For the principal quantum number, N, is determined by the energy level of the electron. Okay, so for P and S sublevels, it'll be whatever row it's in. For D sublevels or orbitals, you're going to use the N-1 designation. I'll make sense of this in class. And for the F sublevels or the orbitals, I call them sublevels, I'm sorry. For the F orbitals, it should be N-2. Okay, again, I'll make sense of this, okay? All right. Okay, the next quantum number is the angular momentum quantum number. It tells the shape of the orbital. So it can be anywhere from 0 to N-1. So N being your energy level, it can be 0 or N-1. So if your energy level is, let's say, 5, you can have anywhere from 0, 1, 2, 3, or 4, and you keep on going, right? But right now we only know of the 3, or we're only talking about the 4 main orbitals, sorry, so we'll only use those. Okay, so for your S sublevel, it can be 0. For your P sublevel, it would be 1. For D sublevel or orbital, it would be 2. And for the F orbital, it would be 3. Okay, so anytime it's an S orbital, you put a 0. Anytime it's a P orbital, you put a 1. Anytime it's a D orbital, you put a 2. And anytime it's an F orbital, you put a 3. Pretty easy. Okay, next one. Magnetic quantum number tells the orientation around the axis. It can go from a negative L to a positive L, so it's based on your angular momentum number. Okay, so for S, it will always be 0 because your S value is 0. You can't have a negative or a positive 0. All right. For your P, it can be -1, 0, or +1. For D, -2 to +2. For F, -3 to +3. And then your spin quantum number in sub S tells the spin, and it can be a +1/2 or -1/2. That's it. All right, so let's put this on a periodic table. Now, I have a copy of this on your notes. You're more than welcome to fill it out on this if you'd like to. All right, so we've already put this on your regular periodic table, but let's locate it again. This is your S sublevel. This is your P sublevel. This would be your D sublevel, sorry, orbital. I have a bad habit of saying that. And then all of these would be your F orbital. Okay, so your S orbital has a angular momentum number of 0. Your Ds will have an angular momentum number of 2. Your Ps are 1, and your Fs are 3. Okay, and if you want to change that, maybe it would be a better idea if we put it as, sorry, I know you just wrote that on your things. Oh, Miss Ruark. Sorry. Okay, let's try that again. All right, so this L would be 0, L would be 2, L is 1, and L is 3. All right, on this one for your M sub L, both of these will be 0, 0. Okay, for your M sub L on these, it would be a -1, 0, +1, -1, 0, +1. Remember, this element goes here. Okay. All right. For your M sub L's on your D sublevel or your D orbital, it should be a -2, -1, 0, +1, +2, -2, -1, 0, +1, +2. And then for your M sub L's on your F sublevel, -3, -2, -1, 0, +1, +2, +3. -3, -2, -1, 0, +1, +2, +3. Okay. Oh, this is one of those freaky ones. There should only be 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. There should only be 14 in this bottom row. Okay. That's okay. It happens. I didn't make the periodic table. Okay. And then your spin. The first electron that comes in will be +1/2. The next electron that comes in will be -1/2. Remember, an S orbital orientation can only hold, that's why I call it a sublevel, it can only hold 2 electrons. All right, so the P sublevel is a parabola, and you can orient that around your X, Y, and your Z axis 3 ways. You can do it one way here, the second way is here, and then the third way is here. It makes it look like a flower. Well, each one of these orientations can hold 2 electrons. And if there's 3 orientations, 2 times 3 gives us 6. So we can have a total of 6 electrons in our P sublevel. All right, so here, +1/2. Oh, no, go back. All right, +1/2, +1/2, +1/2, -1/2, -1/2, -1/2. I know your head is probably spinning right now. It's okay. All right, and then here for your D, the first time through you've got a +1/2. Second time through you've got a -1/2. Why? Because there's a rule that says why. I know, just bear with me. All right, and then the first time through here is going to be a +1/2. Second time through here is a -1/2. Why haven't I told you the rule yet? Because I haven't. It's okay. Just trust me. I know, famous last words, right? Okay, hot mess. I'm going to make sense of it in class. Here you go. I'll see you in class.